Hello friends and welcome to a new session with edupediaworld.com, your favorite portal for online education. Continuing with correlation, today we shall take up the derivation of the formula which we saw in the previous session, and we shall take up the various forms of the formula and see how they were derived. So let's take up the Karl Pearson's coefficient of correlation. To recall, we had seen that the formula to find the covariance, that is the absolute measure of correlation, is given by 1 over n summation xi minus x bar times yi minus y bar. Now let's see how this is derived. We have a scatter diagram where we have the variables x and y as the two axes. And let's say when I plot the values of x and y, I get a scattered diagram like this. Now my values of x are here, and the x-axis, and the values of y are denoted by the axis y. Let me take the mean of x and y. The mean of x let's say is here. Let me call this as x bar, the mean, and say the mean of y is here. Let me call this as y bar. Obviously this point here in the center, the meeting point of these two lines, is your x bar comma y bar. Now we see that we have divided this graph into four quadrants. The first quadrant being here, the second quadrant, third, and the fourth. And we see that most of the values fall in the first and the third quadrant. And we have already discussed that when the data values are moving towards this direction, this is supposedly a positive correlation when it's moving upward towards the northeastern corner, because for an increase in x, the values of y's are also increasing. Okay, now let me take the variation of each individual data from x and y. So let's say the values of x are denoted by xi and the values of y are denoted by yi. So you have xi's and yi's, and when we take the variation or the deviation from the mean, we get xi minus x bar and yi minus y bar. Now this variation, when we take in the first quadrant xi minus x bar, since my x bar is here and the values of xi's are all greater than the x bar in the first quadrant, my value will be positive. Same is the case with yi minus y bar. In the first quadrant they will be positive, so let me write it here that all of these will be positive in the first quadrant. Similarly, if we take the case of third quadrant, both of these would be negative. Whereas if we take the second and the fourth quadrant, in the second quadrant, xi and x bar, xi minus x bar will be negative. Let me write it here, xi minus x bar would be negative, whereas yi minus y bar would be positive. Why? Because the value of y bar is below these values which are in the second quadrant. So obviously the values are above it, so the values are above the y bar, greater than y bar, therefore they'll be positive, whereas they are on the negative side of x bar, therefore xi minus x bar would be negative. It will just be opposite in case of the fourth quadrant. Your xi minus x bar would all be positive here, whereas your yi minus y bar would be negative. In other words, let me just do this once again and show this to you. When I take this as my x bar line, right, when I take on this side of x bar, my xi minus x bar will be positive. This side, my xi minus x bar would be negative. In the same way, say this is my y bar line, so on below the y bar line, the values of yi minus y bar would all be negative, and above this yi minus y bar will all be positive. Is that clear? Now, these are the variations of individual data. So when I add them, when I take the product of these two, I'll get the variation, simultaneous variation or covariation. So I'll have xi minus x bar multiplied by yi minus y bar. Now this will give me the absolute measure of covariation, that is the variation of x and y from their means together simultaneously. So this is your covariation, and obviously we just do not want the impact of number of data to be here, therefore we take the average of this, we divide it by n. So here I get the formula to find the covariation or the absolute measure of correlation. Yeah. Now wherever the data is concentrated, you will have the values accordingly. If it is more concentrated in these two, as in this diagram, you will have a positive correlation. Why? Because we see that the values are positive here in this quadrant. In case if it is more concentrated in these two, then like if you have, say, the data going this way, then definitely when we divide it into the sections like this, we will have, you see that the more data is concentrated in the second and the fourth quadrant. So in this case we will have negative correlation. Okay, so wherever the concentration is, we will have the data accordingly. So this is what we have got here, the formula to find the covariation. Okay, next we had seen the coefficient of correlation, or the Karl Pearson's coefficient of correlation, which is the value of the covariation which we have got here divided by the standard deviation of both the variables x and y. So let's see how we have got this. This in fact is your relative measure or the coefficient. Okay, so we have our coefficient value, the coefficient of correlation denoted by r x comma y is given by covariation of x and y over sigma x sigma y. Okay, now we know that, let me call this as my equation number 1, and of course we have 1 over here, so let me call this as equation number 2. Okay, we have our covariation here. This is the covariation. What is your sigma x and sigma y? Sigma x is given by, if you recall, the standard deviation is 1 by n summation xi minus x bar square. Okay, and sigma y is given by root under 1 by n summation yi minus y bar square. Okay, so let me call these as 3 and 4. Now let me substitute that in equation number 1. So substitute 2, 3 and 4. Substitute 2, 3 and 4 in 1. You get the first basic formula of coefficient of correlation, that's given by 1 over n summation xi minus x bar multiplied by yi minus y bar divided by root of 1 by n summation xi minus x bar square times 1 by n summation yi minus y bar square. Okay, now let me cancel out the n's from here, so we will have 1 by n times summation xi minus x bar times yi minus y bar divided by, now we have one root of 1 by n twice, so when I take them I'll have 1 by n outside, and then summation xi minus x bar square times summation yi minus y bar square. These two will cancel and we will have the first type of the formula which we had discussed previously. So we'll have summation xi minus x bar divided by root of summation xi minus x bar square times summation yi minus y bar square, and let me call this as 5. Okay, now this is exactly what we have here. Okay, how did we get the next type of the formula from here? Let's work it out. Okay, let's take the numerator alone from here. The numerator is summation xi minus x bar times yi minus y bar. Okay, let's split this. We will have summation xi minus x bar multiplied by yi minus summation xi minus x bar times y bar. Y bar being a constant can be taken out of the summation, so we will have summation xi, and here of course we can multiply this to both the terms, so we'll have summation xi multiplied by yi minus summation yi times x bar minus, here we will have summation xi minus x bar times y bar, which is outside. Okay, so just pay attention once again. What I did is I took the product of this xi into yi, that's here the first term, and then minus I have a summation x bar, so summation x bar multiplied by this second term yi. Okay, and here I have just taken this outside the summation sign because this is a constant. And if you recall, this is what we did when we derived the alternate formula for standard deviation. Okay, now what will happen to this second term? If you recall, this part of the second term will be equal to 0. Why is it so? It's from the property of arithmetic mean. Yeah, recall arithmetic mean. Here this is the sum of the deviation from the actual mean. Sum of the deviation from the actual mean, and the property says that this is equal to 0. Therefore this whole second term is equal to 0, and I'm left out just with this part. So I'm left out with summation xi minus xi yi minus, again here this x bar is a constant, so I can take it out and I'll have summation yi. Yeah, if you want you can write it further as summation xi yi minus x bar times, now the summation yi, we know the average of y is given by summation yi divided by n. So from this I can get that summation yi equals n times y bar. Yeah, of course we can write it, so therefore we can write this as n times y bar. Okay, let me call this as number 6. In the same way we can take the denominator now and work it out. And you know that the denominator is nothing but the standard deviation, which you have already seen. So let me just do it. You have the denominator as summation xi minus x bar square, right? The denominator. So this can be written as summation xi minus x bar multiplied by xi minus x bar, and I'll do the same thing here. I'll take the first term, multiply it with xi first, and then minus x bar times this. So I'll have summation xi minus x bar multiplied by xi minus summation xi minus x bar times x bar. X bar being constant can be taken out, and here this can be further split by multiplying it with this term. So we'll have summation xi into xi minus summation xi into x bar minus this term. Again, if you see, I have x bar times summation xi minus x bar. Automatically this is again using the same logic, same property, this will also become 0, and this term will become equal to 0, and by the virtue of this the whole second term becomes 0. So I'm left out just with this. I'll have summation xi square minus this being constant. This is a constant, so it can be taken outside the summation sign. So we'll have x bar times summation xi. Okay, now using the same logic here for x, I can write it further as summation xi square minus n times x bar square. Let me call this as my equation number 7, and working in the same way for the second part of the denominator, which we have as summation yi minus y bar square, I'll get summation yi square. Now the working is same as we have here for x, so it will be summation yi square minus n times y bar square, and let me call this as equation number 8. Okay, so now I have 6, 7 and 8. Let me take all of these three and substitute them. Substitute 6, 7 and 8 in the previous form, that is the one here, which is your equation number 5. Okay, so what we'll have, this will be the numerator will become summation xi yi minus n times x bar y bar divided by, we have root, so root under first form is summation xi square minus n times x bar square multiplied by summation yi square minus n times y bar square. Okay, so this is another form which you have, which you can use to work out the problem, but then this was not the exactly what we were intending to. Let me call this as 9. This was not something which we were intending. What we have got here, the final form, is this, and that we will get simply by rearranging this. So when you rearrange this, let me take it separately now. You have Rxy as summation xi yi minus n times x bar y bar divided by root under summation xi square minus n times x bar square, and then summation yi square minus n times y bar square. What I can do is I can write my x bar as summation of x by n and y bar as summation of y by n. So I'll have summation xi yi minus n times summation x by n and summation y by n divided by root under summation xi square minus n times summation x by n the whole square, because we have x bar square, so I'll have a square both in the numerator and denominator. Further, for y we can write it as summation yi square minus n times summation y by n the whole square. I can cancel out the n's, okay, and then I'll be left just with summation xi yi minus summation x summation y by n divided by root under summation xi square minus summation x by n, and then here we will have summation yi square minus summation y square by n. Further, multiply this, multiply both the numerator and the denominator by n. We know that if we multiply both the numerator and the denominator by n, it's not going to change. So once you multiply, you will have, when you multiply the numerator, you'll have n times summation xi yi minus n times summation x summation y by n divided by root under, now we have a root, so of course when you multiply by n, one will go, a complete n will go inside the first root and inside the second one, so root of n and root of n will make it n. So we'll have n times summation xi square minus summation x n times summation x by n square, and same is the case with y, so we'll have n times summation yi square minus n times summation y square by n. Now what happens, these will cancel out each other, yeah, and you're left with the final form of the formula which we intended to derive, which is n times summation xi yi minus summation x summation y divided by root under n times summation xi square minus summation x square multiplied by n times summation yi square minus summation y the whole square. So this was the formula which we were intending to get. Yeah, this is the final form of the coefficient of correlation, or the Karl Pearson's coefficient of linear correlation. Okay, I hope this working will help you in understanding the formula and in remembering the formula. It's simple, and of course you can use any of the forms which we came across during working. Maybe to start with, you can have this formula. This is the best way to remember. This is by definition. Then just by applying the just by simple substituting the values of covariance sigma x and sigma y, I get my form here, which is this one. That is my second formula. Then moving further, when you work out, you have several intermediate steps. You can remember it either in this form or in the form here, or maybe the last one. To keep it simple, it's always better just to remember one form of the formula, keeping in mind the way it has been worked out. Okay, I hope this working will help you. Now, just to consolidate and check your understanding, let's take a problem. We have already discussed the problem in the previous session and I had shown you the working. So this is for you to solve, and so you can pause me for a while and check your understanding by solving this. Find the Karl Pearson's coefficient of correlation of the given data. Alright, so let me now work this out for you. I hope you must have done it, so maybe you can check your working with that of mine. Let me use the first form of the formula here. For the first form of the formula, what we need is, first we need the mean average, so let me very quickly find that. The sum of the values of x is 30 and the sum of the values of y is 40. We know the counting. If we count, we have 1 2 3 4 5, so my mean or average arithmetic mean of this will be the value here divided by 5, and in this case it will be the value here, that is 40 divided by 5, which is 8. So the means are 6 and 8. Then I need xi, I need x minus x bar, let me write it x mean, and I need y minus y mean. Okay, so the mean this will be 6 minus 6 here because the mean is also 6, and here it will be 9 minus the mean, which is 8. Okay, next I need the square of this. X minus the mean of x raised to power 2 and y minus the mean of y raised to, this will be the square of the term here, and this would be the square of the term here. Okay, now I can drag down together for all the 5 cells in these 5 columns, 4 columns here. Yeah, so I have the values being there. Now next I need the sums of all of these. I need the sum of this both the squares, and that's here. And you see that the sum from the actual mean of x and y is 0, and that will always be the case. Next I need the product of xi minus x bar and yi minus y bar. It's x minus the mean of x multiplied by y minus the mean of y, and this will simply be the value here multiplied by the value in this column. And then taking the sum over this, I get minus 26. Now to find the correlation, recall the formula. It's simple. I have summation xi minus x bar, which is this. This is my summation xi minus x bar. This will be a numerator, and denominator is the square root of the product of the square root of these two terms. So these two are my denominator. Okay, let me give them another color. Okay, now my correlation value will be, in fact, the Karl Pearson's coefficient of correlation will be equal to this value divided by square root of this multiplied by square root of this number. Okay, this whole is in the denominator, so let me put that, the whole of denominator, in one parenthesis, and that's our correlation. And you see that this time the correlation happens to be negative, and of course the absolute value, that is the covariance, was also negative. So quite obviously the coefficient of correlation will also be negative. Okay, now let's very quickly do the same problem using the second type of the formula, where we have x multiplied by y. We need the square of x and we need the square of y. So first column you'll have the product of this and the column y, then it's x raised to power 2, and here it is y raised to power 2. Okay, dragging them down till the last value here. Yeah, we have all of these, and then let's take the sum over all of these. We know the values of the sum of x is 30 and y is 40. The rest of these we get here. Next, if you recall the formula, the second form of the formula is, in the numerator you have summation xi yi n multiplied by summation xi yi. Let me put the numerator with this color. Okay, minus summation x minus summation x multiplied by summation y. So these are the numerator. Let me calculate the numerator together here. Numerator you will have n, which is 5 in our case, multiplied by this number here xi yi minus the number here into the number here. Yeah, so this is our numerator, and then denominator, we have two denominators. Denominator 1, let me write in denominator for x will be square root of n, which is 5, multiplied by summation x square, which is 220, minus summation x the whole square, which is 30 raised to power 2. Okay, and then we have denominator for y, which is equal to, again the formula is the same, the structure of the formula is the same. We have square root of first n, which is 5, multiplied by the y square value minus summation of y raised to power 2. Okay, so now our correlation value will be this numerator divided by the product of the denominators. voila, you see that the values are the same as we got in the previous method. So that's about the working of correlation problems. By now I'm sure you must have understood and consolidated your understanding on the working of a problem on correlation. That's all we have in this session. In the upcoming sessions we shall take up the shortcut methods, and then we will move to Spearman's rank correlation. Keep watching Edupedia World videos. Thank you.